Sigma and factorials. So we are going to take a look at these two things, which are condensed notation. So the first one we're going to take a look at is factorials. Factorial notation is an exclamation mark. You might have seen this before. So a factorial is a simplified version of multiplying consecutive integers. So a factorial is just a simplified form of multiplying consecutive, and I shouldn't actually say integers, they are whole numbers. Every calculator has a factorial button, and so what it does is instead of writing 1 times 2 times 3 times 4 and then multiplying it all out to get 24, you can actually write 1 times 2 times 3 times 4 as 4 factorial, that's that exclamation mark, and you can find that button on your calculator. On most calculators, it's pretty easy to find. On the graphing calculator, it's a little bit harder to find. You will have to find your math button. You will then go to the menus across the top. I think it's the far right one that says probability. And underneath there, you will see a drop-down menu that will find your factorial button for that one. So you have to dig a little bit for it on the graphing calculator, but on all your sort of regular scientific calculators, it is right there. So the definition of a factorial, if you want the mathematical definition, is that n factorial, n being a whole number, will be n times the number before it, times the number before that, times so on, so on, so on, all the way down to 3 times 2 times 1, and the last number is going to be 1. Also by definition, 0 factorial, because it has to be, is equal to 1. It really doesn't make a whole lot of sense, and that's why it's defined. It's essentially because it has to be. And I will show you one example of where you're going to be using that. So factorials can be found in many, many places. One example is in Pascal's triangle. So when we were doing Pascal's triangle for expanding, and I will possibly use this in calculus as well, but when we were using Pascal's triangle for expanding something like a plus b to the power of whatever, right? A plus b to the power of n, we knew that a plus b to the power of whatever it is that we're going to be dealing with, n, followed this triangle that was 1, and then 1, 1, and then 1, 2, 1, and then 1, 3, 3, 1, and we found those middle numbers by sort of counting down towards these things. The 1 plus the 2 was the 3. So for example, if I had to do a plus b to the power of 4, it was 1a to the 4th and 0 b's. It was, or add those together, I would get 4a cubed and 1b. Add those together, I would get 6a squared and 2b's. Add those two together, I would get 4a and a b cubed. And then that last one would be no a's and all 4 b's. So I'm writing this, the no b's situation here, like with the 0 sitting up in the corner for the a and the b like this. So you can see that in this binomial expansion, the a's are counting downwards and the b's are counting upwards. Well, factorials also help. So to deal with a factorial for a plus b to the power of 4, what this really actually equals in this little case here is this number 1 that you have at the front is equal to 4 factorial divided by 4 factorial times 0 factorial. So 4 factorial is 4 times 3 times 2 times 1, which is 24. 4 factorial on the bottom is also 24, and 0 factorial is defined to be 1, so you're going to get 24 over 24, which is 1. And you would get a to the power of 4 and b to the power of 0. So remember that we are expanding a plus b to the power of 4 here. Okay, so that's what we're getting here. For the next coefficient that we're dealing with, to get the 4 here, you would still start with 4 factorial, and the 4 comes from adding all your powers together, but there are 3 a's and 1 b. So I want you to see how this works. You've got a to the power of 3 and b to the power of 4, or b to the power of 1. 4 factorial, again, is 4 times 3 times 2 times 1. It's 24. 3 factorial is 3 times 2 times 1 is 6. So 24 divided by 6 gives you that 4 that you're dealing with here. It's the same for this one. So for this one, because we're expanding something to the power of 4, we get that. We've got 2 a's and 2 b's. A squared, b squared. So when we're calculating this, 4 factorial on the top is 24. Here, why don't I write that out so you guys can see this. This would be 24 divided by 24 times 1, which is 1. A to the 4th, b to the 0. This one is 24 divided by 6 times 1, which is 4. A cubed, b to the 1. This one is 24 times, divided by 2 factorial, which is 2 times 1. And 2 factorial, which is 2 times 1. 24 divided by 4 is going to be 6. A squared, b squared. And so you can keep going on and on like this. The factorials are useful because what you can do then is you can start talking about, for example, expanding a plus b to the power of, like, say, 10. And so your first term would have a 10 factorial and 10 factorial, 0 factorial. And that's because you have 10 a's and 0 b's, and so on and so on and so on. So if I wanted the 5th term, let's say, for example, of this expansion, I want you to notice that in the 5th term, we would actually only have b to the 4th, because we're starting counting our b values. If you start counting here, you're starting counting at 0. So if you count 0, 1, 2, 3, 4, that's 5 terms. So that tells us that because my powers have to add up to 10, I'm going to get 6 a's. And the number in front is going to be 10 factorial, which is my total number, 6 a's and 4 b's. And you can actually just find the 5th term, random term, even if we wanted to expand something like a plus b to the 1000, and you wanted to find the 5th term or the 15th term or something like that, you would still be able to find that without having to draw your Pascal triangle. So that's one thing that you can be using the sigma for, the factorial notation for. So sigma, this is our second one, is a condensed or simplified version of adding things together. So factorials, we're multiplying stuff together, and sigma is going to be adding. So sigma essentially means sum. The sigma notation looks something like this. This is a capital Greek letter F, or S, sorry. And we usually start talking about from k equals a to b of some function in terms of k. So sometimes there's a bracket around it or sometimes not, but the sigma doesn't exist without its little function. So f of k is a function that determines the pattern. What we are going to do to expand a sigma and see what it actually looks like, we plug in all the values of k from a to b into the formula. And that formula is f of k. We then add, sigma means sum, all the terms. So sigma is a very, very big deal as you move forward into calculus. So we do need to be able to think about what we're going to be dealing with when we expand a sigma. One of the things to note, if you wanted to calculate the number of terms in a certain sigma, the number of terms, the total number of terms, is equal to b minus a plus 1. Because essentially, you take the difference between the b and the a, and then you add 1 for that first term. Okay, so let me show you a couple of examples. Here's your first one. It will say expand or something like this, but do not evaluate. And it's really just making sure that you understand what that sigma means. So let's say I went k equals 1 to 3, and the formula that I'm going to be using, or the function that I'm going to be using, is 2 to the k plus 1. Essentially, what you have to do is you have to take this function right here, and you have to plug in k equals 1, you have to plug in k equals 2, and you have to plug in k equals 3. We start with the bottom number, we finish with the top number. The bottom number is not always going to be 1, so beware of that. And so when we plug these numbers in, you're going to end up with 2 to the 1 plus 1 as your first term. Sigma means sum, so you're going to put a plus sign there. The next one you're going to get is 2 to the 2 plus 1. Sigma means sum, so you're going to put a plus there. The next one you're going to get is 2 to the 3 plus 1. So that's essentially just expanding the sigma. If you really want to get technical, 2 to the 1 plus 1, that's going to be 3. 2 squared plus 1, that's going to be 5. And 2 cubed plus 1, that's going to be 9, right? So we're expanding but not evaluating. Obviously, to evaluate, you just add them together. Okay, so the second type of question that you might want to do is you might want to do a question that just says simplify. And I thought I'd bring something else into this as well, and so that you can see the types of sort of combination questions that you might get. And it says the sigma as k goes from 1 to 20 of, let's say, log of k. Ooh, the logs are in it. So we aren't going to actually plug in all of these because it gets very, very long. But let me show you what it looks like when I expand the first one. It's going to be log of 1. So I'm plugging in k equals 1. And then plus, because sigma means sum. Log of 2, and then plus. Log of 3, and then plus. And goes on and on and on until you plug in log of 20. So you start by plugging in k equals 1 right here, and then you plug in k equals 2, and then you plug in k equals 3, and so on until you finish by plugging in k equals, 20. So now, to simplify this, we can maybe use some log properties, because logs and sigma really, really go well together. When you're talking about logs and sigma, you've got yourself these plus signs in between all of your logs, and they all have the same base. And when we have those plus signs in between our logs, what we're really doing is we're really multiplying. So you've got the 1 times the 2 times the 3 times ... all the way up to 20. Or even more fun than that, 20 factorial. And that's maybe an expression that you might see for simplifying the sigma as k goes from 1 to 20 of log of k. You also may be asked to evaluate, and this would be without a calculator. Maybe we have sigma as k goes from -1, let's change it up to 5, of log base 2 of k plus 3 over k plus 2. So this one's a little bit more in-depth because we're actually going to evaluate it. And when we do evaluate, unless we can see a pattern, you are going to have to plug in all the numbers. But the first k we're going to plug in is going to be at k equals to -1. The second number that we're going to plug in is going to be at k equals 0. It's the next number up. And then k equals 1. And then k equals 2. And so on until we finish with k equals 5. Each term will have a plus sign in between, right? So we'll keep going here as we go through. Let's see if we can see the pattern. So I'm going to get log base 2 of -1 plus 3 is 2. -1 plus 2 is 1. And then we have a plus sign. And the next one is going to be log base 2 of, we plug in 0, 3 over 2. And then what we're going to get is we're going to get log base 2. We're going to plug in 1. 1 plus 3 is 4 over 3. And we're going to keep going, and we're going to keep going with this pattern. Now, if you can see the pattern, you don't have to really keep plugging in these numbers. The next one, if you take a look at the top numbers, 2 and 3 and 4, this is going to be log base 2 of 5 over 4. You can keep plugging it in, and so on until my last term that I'm going to be dealing with is going to be log base 2 of 5 plus 3, which is 8, over 5 plus 2, which is 7. Now this looks like a great big mass, but remember, when there are plus signs going on in between all of our logs, it really means that we are multiplying. So let's see what we get when we multiply. Log base 2 of 2 over 1 times 3 over 2 times 4 over 3 times 5 over 4 times, and you can keep going if you really want to see it. I can write them all out, that's okay. What's that going to be? 8 over 7. That's going to be all of them if I did them all. Don't actually try to multiply these things out. I don't really want to see 8 factorial over 7 factorial. I mean, you could if you really want to, But notice that these guys cancel. The 2 cancels with the 2, the 3 cancels with a 3, 4's cancel, a 5 cancels, a 6 cancels, a 7 cancels. And what this turns out to be is log base 2 of 8 over 1, which is 8. And as we hopefully remember, log base 2 of 8 is 3. So these are a couple of examples of how sigma can be used with logarithms especially, but it's going to be used in a lot of other places as well throughout this course that we're dealing with. Factorials are also sort of pop in here and there, so it's good for us to be familiar with that as well.